A common application of exponential functions is half-life. So if I wanted to find the half-life of an element, then I can say whatever the element is, whatever my original element amount, so let's say this is my initial, times e to the RT would equal what's left. So if I said there was half left, then this amount, let's say, would be 100. This could be 50. And when I went to solve this, I'd divide both sides by 100, and I'd always end up with 1/2 on the other side of my equal sign. So we can simplify our equation to say that 1/2 would equal e to the RT. Now t is still time and rate is still r. So if it tells you that it takes 14 years for some element to decay to half the amount, or the half-life of a certain element is 14 years, then I would say that 1/2 equals e to the r, which is what I don't know, t, which I do know, 14. Now this goes right back to what we just spent time doing, which is solving exponential functions. So I'm going to ln both sides of this equation. The ln of e cancels and I get 14r equals ln of 1/2. Divide both sides by 14 and then let the calculator do the work. So ln of 1/2 divided by 14 tells me that this rate is negative 0.049 or 0.05. Now it should be negative because this is a decaying rate, so it should be negative. And that decaying rate in percent would be 5%. So then if it went a step further and said, now if it had gone a step further and it said for that same element, if I started with 330 milligrams of that element, whatever it is, how much would be left after 20 years? So now I'm going to use my a sub 0, which is now 330, times e to the RT. Now r is back in decimal form and it's negative, and t is 20. And then again, let the calculator do the work on that. So 330 e to the negative 0.05 times 20. And you would have left 121.4 milligrams of that element. Another way you can see half-life is if it asks you, it gives you the rate. So let's say, again, it says, what is the half-life of that element? So now we're looking for t. So I know that it's 1/2 equals e to the r, which is 0.025, and it's decaying, so it's negative, times t. So I'm going to ln both sides of the equation. I'd get ln of 1/2 equals ln of e, cancels, negative 0.025 t. Divide both sides by negative 0.025. And again, let the calculator do that work. So ln of 1/2 divided by negative 0.025. And I get t equals 27.7, and this could be years. All right, that's a little glimpse into half-life. Now let's say we're looking at the double life. And a lot of times this deals with population. So again, if it said something has a population of 10,000 and it grows at a rate of 2.7%, how long would it take to double? So I would know it's 20,000 on the left, 10,000 on the right, e to the r, which would be 0.027 times t. Now, my first step is always going to be to divide by the initial amount, and because it's doubled, this side will always be 2. So now we can simplify our equation and just say that it's 2 equals e to the rt when we're talking about double life. So now I would say I would either know, like we do this time, the rate, or we would know the time, and then we would solve our equation. So ln of 2 equals ln of e to the 0.027t. The ln of e cancels. 0.027t would equal ln of 2. Divide both sides by 0.027. And I'd get ln of 2 divided by 0.027. And time is 25.7 years. So that's how long that population would take to double. Just like with half-life, we can do the same applications with double life. So you can either be given the rate and you're looking for the time, or you can be given the time and you're looking for the rate.